Okay, so let me go back now to the issue that we discussed last time, and in particular on again on decision making, and in particular I introduced the problem where different objective function can be defined, and in particular different objectives. And I said that the most convenient way of dealing with different objectives is to try to combine different objective functions, therefore to assign to each objective an objective function and try to combine the different objective functions to obtain just one resulting global objective function. In doing so, of course, you have the obvious way of making this is to sum the individual objective functions, and in order to obtain a meaningful global objective function, we should make sure that the different and individual objectives are rescaled so that they are comparable. For instance, we may make them varying in the interval 0, 1, and the rescaling is quite simple. Usually, if you can define a maximum and a minimum value for any objective function, then you can rescale by simply dividing the objective function for the maximum value. For instance, if it is positive 1 and therefore has a minimum to 0, if you divide any objective function for the maximum value, you obtain a resulting objective function that can vary between 0, the minimum value, and 1, which is the maximum. But besides then rescaling, you should also evaluate, once that you made the three objective functions comparable each other, you should evaluate what is the influence, the weight that any objective function has with respect to the others. Therefore, if you combine an objective function like, we can call it MB star, depending on a decision plan X, you can compute the sum of the two individual functions, NB1X plus NB2X plus NB3X, where these individual benefit functions are already rescaled so that they are comparable. Sometimes it might be difficult to identify the maximum value for an objective function, but in any case, at least in principle, you can identify a maximum and then you can make this objective function comparable. Now, if you just sum them in this way, once that you made them comparable, this means that you assign equal importance to each one, NB1, NB2, and NB3. You assign equal importance. So, this might be appropriate in some cases, but in other cases might be not. For instance, because you want, for instance, if you want to give more weight to the first objective function with respect to the other, you may want to introduce what we call weights. What are weights? Weights are constants that are introduced in this expression to give different emphasis to each one of these individual objectives. And therefore, you can write the sum in this way: W1 NB1 X plus W2 NB2 X plus W3 NB3 X. And usually, we put the condition for weights that W1 plus W2 plus W3 is equal to 1. Usually we put this condition. And therefore what you obtain for the resulting objective function is a weighted average, media pesata in Italian, of the three individual objectives. And this is useful because it allows you to give different importance to the individual objectives. For instance, you may say that W1 is equal to 1, and therefore this implies that W2 and W3 are equal to 0, and therefore you compute the resulting objective function by giving just weight, just importance to MB1, and you discard MB2 and MB3. This can be the case. For instance, if you, for some reason, if you start from 3 objectives, but you want to consider also the case in which you consider each one individually alone. Or if you give equal value to the 3 weights, therefore 0.33, 0.33, 0.33, you give equal weight, and then you go back to a situation which is equivalent to the first one, where we just take the sum of the 3 objectives. Now the problem is, okay, this is a nice option, is a nice feature. The problem is, how can we evaluate these weights? How can we estimate W1, 2, and 3? And we must take into account that the value of the weights is subjective in many cases, because if you have different objectives, in many cases, I would say in all cases related to water resources management, it is subjective to give more weight to, for instance, environmental protection with respect to, for instance, water supply for civil use. In some cases, you have laws that help you to identify the weights. For instance, in Italy, we have the law that says that the civil use is a priority. And therefore, if, for instance, you have objective functions related to benefit that we gain for civil use and benefit that we gain from industrial use, even if, in principle, if you reason in economical terms, the industrial use is more valuable, we have the law that says that the priority is the civil use. This means that the civil use must be satisfied first, and then you evaluate what might be the amount of water that you deliver for industrial use with respect to agricultural use, for instance. So in some cases you have the laws that allows you, help you to identify the impact of any objective, but in other cases you don't have the laws suggesting, and therefore you have to rely on your individual judgment. Or, if we want to act in a transparent way, you have to interview people, ask them their opinion, and then you have to put all the opinions together, and this is a very difficult task for which we need a lot of vision. So usually, in this, when dealing with these problems, you have to meet people, and you have to collect different opinions, and then you have to come up with a solution that is not satisfying for anybody, because of course the compromise, strictly speaking, disappoints everybody, but it's anyway a better compromise solution. And to identify the synthesis, to synthesize different opinions, as I said, is a difficult task. So it's advisable that you make use of transparent tools and objective tools to try to identify the best opinion. And therefore I want to give you an example of a very simple way to identify these weights if you have different objective functions. And this tool which I'm talking about is called Pairwise Comparison, which means that you compare the different objectives one by one, meaning that you compare two objectives at any time, and therefore your comparison is easier. So, And you see here, alternatives are compared with subsequent pairwise comparisons. And in practice, the technique works in this way. If you have more than two objectives that you have to analyze and to quantify the importance, you compare the objective. I think the correct terminology in English is one by one, which means that you compare two objectives each time. And therefore, if you have three, you compare objective 1 with objective 2, and then objective 1 with objective 3, and then objective 2 with objective 3. This is pairwise comparison. So how can we compare these objectives with these different objectives? We need guidelines, of course, and the guideline is given by this method, which is called the SATI, from the author, the proposer, pairwise comparison. SATI proposed a table, which you can see here. Okay, first of all, let me introduce the example, and then the table. Let's suppose that our problem is characterized by three objectives, and it's just an example. So let's say that the objective are the recipient for the benefit for the recipient, so the benefit for an individual, and then the second objective is an institutional benefit, which means benefit for the government, for instance, and the third benefit is the societal benefit, so benefit for the society. And then, as you can read here, we have three benefits to which we have to assign a weight to compute a resulting total benefit. Here I made a mention to one technique, the Pareto analysis, that can be used to help us in this identification problem. I'm not giving any more detail on Pareto analysis because I don't want to be too much technical. While I want to dig more detail, I want to give more details on this pairwise comparison. Let's see if I have to shut up the PC or not. It's just the image that is not working. Okay, just 1 second. Just 1 second, it's better if I restart. Yes. Basically, the tables, as you will see, proposes a kind of score to give to one objective with respect to the other. So you are asked to compare, for instance, the recipient benefit with the societal benefit, and you have to say what is the importance, in your opinion, of the recipient benefit with respect to the societal benefit. And there is a scale of numbers that you can use to quantify this importance, a suggested scale, and therefore by comparing the alternatives one by one, you obtain a final estimate for the weights with some problems that we will take into consideration. So let's see if we can get it. Should work now because it's a frequency problem. Okay, here it is. So this is a table that I was mentioning to you. So you have two activities, two objectives to compare. If you think that they have equal importance, then you assign a score of 1, which means that, in your opinion, for instance, the recipient benefit with respect to the institutional benefit has a score of 1, which means that they are equally important. Moderate importance, which means that experience and judgment slightly favor one activity over another. So if you say that the recipient benefit has a score of 3 with respect to the societal benefit, it means that you favor moderately the recipient benefit with respect to the societal one. Strong importance, very strong, extreme importance, and then you have, of course, compromise values. You can use reciprocals. For instance, if you say that the recipient benefit is 1/3, as a score 1/3 with respect to the societal benefit, it means that the societal benefit is moderately important with respect to the recipient benefit. We will see an example later on. Okay, so let's see, for instance, an example of table. The table must be read by rows. So we have to create, not a table, a matrix, sorry, a square matrix where you put in each row and in each column the individual objective. So you see recipient benefit, institutional benefit, societal benefit, and even here, recipient, institutional, and societal. And let's read it, as I said, by a row. So the recipient benefit, with respect to the recipient benefit, of course, the score is 1, because they are the same objective, so they have the same importance. And let's suppose that we decide that the recipient benefit, with respect to the institutional benefit, has a score of 3, which means that it's slightly more important. And then let's say that the recipient benefit, with respect to the societal benefit, has a score of 5, which means much more important. Then we can go to the second row, and then when we compare the institutional benefit with the recipient benefit, we have to use 1/3. The matrix must be symmetric, because we use the score of 3 to quantify the importance of the recipient benefit with respect to the institutional one, and therefore, for coherence, we have to say that the institutional benefit is 1/3 with respect to the recipient one. So the matrix must be symmetric. And then you have 1, of course, on the diagonal, and then we have to evaluate something that we didn't evaluate so far, which is the importance of the institutional benefit with respect to the social benefit. And we could say that it's 3, for instance. You can write whatever you want, but you must take care to use reciprocals to make the matrix symmetric. And then, for the societal benefit with respect to the recipient, we say 1/5, because for symmetry. And then, societal benefit with respect to institutional, 1/3 for symmetry. And then 1 along the diagonal. Okay? Now, let's observe that it's not just sufficient to ensure symmetry, to make the overall evaluation consistent. In fact, look at the example that is given here. The evaluation given by this square matrix is inconsistent in what? If you consider that RB, recipient benefit, is as a score of 3 with respect to the institutional benefit, and you consider that the recipient benefit has a score of 5 with respect to the societal benefit, then you would expect that a score of 3 to the institutional benefit is equivalent to a score of 5 to the societal benefit. Namely, institutional benefit has a score of 5 over 3 with respect to the societal one, and not 3. Okay, so this evaluation is inconsistent, but inconsistency can be tolerated. The method works anyway. If the matrix is symmetric, the method works, but you must be kind of aware that inconsistency means that in expressing your opinion, your feelings, you just were not consistent. So the resulting weights are also affected by inconsistency. We will see in the next slide how to compute weights, and if you have inconsistency in the matrix, you have also inconsistency in the weights. There are methods, analytical methods, to evaluate inconsistency with also suggested thresholds, like methods that say, look, let's compute this index to evaluate inconsistency, and if the index is greater than a limiting value that is given, then please go back to your decision matrix, evaluation matrix, and try to make it more consistent, because the inconsistency is too high. We are not going into the details, just let's take for known that we have some inconsistency tests that can be performed. Okay, now let's accept this evaluation and let's see how we can compute the weights. There are two methods. The simplest one is what is given here. The method suggests to rescale each column so as to make the sum of each column equal to 1, which means that in this case the sum of the column is 1 plus 1/3 plus 1 over 5, which is more than 1, of course, and then you have to reduce proportionally each score so that the sum is equal to 1. You have just to divide each score by the sum, by the resulting sum, and then you rescale. So you rescale each column so that the sum is equal to 1, and then you compute for each row the average. Okay? So in this case, you get the weight that gives to the recipient benefit a value of 0.64, which means that the recipient benefit is relevant. Because given that the sum of the weights is equal to 1, you see that here a very relevant importance is given to the recipient benefit. This is to be expected because we gave to the recipient benefit a score of 3 and 5 over the other two benefits, which means that we thought that the recipient benefit is more important, and therefore we may expect that the weight is high. And then the other weights are 0.26, 0.11, which means that the societal benefit is not very much important for us. And this is to be expected because you see that the recipient benefit, we gave a score of 5 with respect to the societal benefit. So we thought that the recipient benefit is much more important than the societal benefit. And also, if you look at the institutional benefit with respect to the societal benefit, is more important. And therefore, of course, we have to expect that a kind of ranking like this, where much of the importance is given to the individual benefit and then to the institutional and then the societal. And you see that this is a very simple way of finding weights. This is accordingly to your opinion, of course, but this can be done also individually with people. You may interview people individually or even collectively. And because, you know, it's much more better to agree on a series of simple problems than to agree on a complex problem. If you just ask people, let's decide the weights directly, people don't agree each other. Because of course anyone looks at its individual benefit. Instead, if you split the complex problem in many simple problems, first of all, people do not immediately see the final result, and therefore they try to use wisdom to make the evaluation, not just convenience as a driving principle. But if you don't see the final result, you just use wisdom with respect to maximization of the results. And also, if you split a complex problem in a simpler one, it's easier to use wisdom. What we would like to reach is that people use wisdom rather than individual benefit. And therefore, if you split the complex problem in simple ones, to use wisdom is simpler, of course. And there is also a second method. You can rescale the columns like before, and instead of computing the average, you may find the value that has the least distance from the rescaled value in each column, because the average is just a way to compute, of course, a compromise value between three individuals' contributions. But you could also define a distance in some way, for instance, the squared difference between the result and each individual element of the sum, and then minimize the distance. This is not very much important for us to know. Let's assume that we stick on this method, which is simpler to remember. Just compute the mean. Okay? And if you think about a problem with many objectives, like 10 objectives, of course, the advantage becomes more evident. Because if you have 10 objectives to identify 10 weights, really, if you put all of them together, it's very complicated. While if you compare one by one, the different objectives is easier. It's a long process, because of course if you have 10, it's a long process, but in any case, it's easier. 1 second. I think it was finished. Let me see if it was the last slide. Okay, it's not really the last, because in the last slide I provided a consistency test. Let's forget about it, okay? Let's just assume that we know that there are tests for consistency, but let's not go into the details, because you see, it's quite simple to compute the statistics, but then eigenvalues are involved of the matrix, which is already something that is too much mathematically detailed. Okay, so this is a way to combine different objectives. There are other ways, like Pareto analysis, as I mentioned, but I wouldn't go into more details, and I would close this part on decision theory and decision criteria, while now I would like to move to another issue. Let me wait a little bit before opening the next PowerPoint, which is decision under uncertainty. What does it mean? What does it mean, decision under uncertainty? Unfortunately, decision theory sometimes is suboptimal, is not optimal for us, because what we have taken into consideration so far are methods that implicitly assume that you can define exactly your objectives, and in particular your objective functions. So this means that we assume that we are able to define the objective function with an exact solution. This is not the case in water resources management. You always have to deal with uncertainty, and therefore your objective function is defined in some way, but there is uncertainty there. Uncertainty means, for instance, that if you consider an objective function like the one that we already considered, mbix equal to ai, which multiplies 1 minus 2 to the power of minus pi xi. If you consider an objective function like this, uncertainty means that a and b are not exactly defined, but they are uncertain. Uncertain means, for instance, that you don't have an exact value for A, but you have a probability distribution. You are forced to consider A as a random variable, and therefore you don't have a unique value, but rather a probability distribution, which has, for instance, an average, so an expected value, but not an exact value. And therefore the question is, when I am in these conditions, can I still apply the methods that I have considered so far? In particular, can I still apply Lagrange multipliers? Can I still apply other methods? What should I do in the presence of uncertainty? First of all, uncertainty, you know, because I already mentioned to you about uncertainty, that is always present in hydrology and is probably unavoidable. I say probably because I mentioned to you that this is also a philosophical discussion that the scientific community is engaging about the possibility in the long future to eliminate uncertainty from hydrology. And basically I think that this is not possible, because, or if it's possible, it's not possible for us within our lifespan. Because, you know, hydrology is, in my opinion, affected by randomness in any case, and therefore uncertainty is always present. There is, of course, a part of uncertainty that can be reduced. For instance, the uncertainty related to the monitoring techniques that will improve in the future. So we will be able in the future to measure rainfall, for instance, much more precisely than we can do now. But I think that in any case, there is a part of uncertainty whose importance is varying depending on the process that will never be eliminated. And therefore is something that in water resources management is always present. Now, what can we do when, in this case, the parameters of our objective function are uncertain? Basically, there are two options that are obvious in order to be able to still use the techniques that we have considered so far. The first option is to use the expected values. So if you don't know exactly A, you take the mean and you work with the mean. Because the expected value, of course, represents a very likely situation. Very likely, which means that the situation represented by the mean is highly probable. So one possible solution is to adopt expected values and to assume that they are exact, that they provide a good representation of the real situation. Another obvious solution is to use safe values. So one option is the average. A second option is to use safe values. Like if I want to estimate the best decision to be taken, let me assume exact values for the variables, like for A, and let me take a value that in any case makes me safe, makes my decision safe. Of course, you understand that safe decisions are never convenient. When you take a safe decision, this is never a convenient decision. Usually, the most convenient decision is a risky decision. And even in design, if you want to be safe and you increase your safety factors, which are also called in hydraulics allowance for freeboard, if you increase the safety factor, then you get structures that are overly sized and therefore cost more. But what is even more important to say is that these two options, use expected values and use safe values, are not optimal. In some cases, they are absolutely inefficient. And let me make an example which does not refer to water resources management, but I think is extremely interesting it's an example that is taken by statistics, and the statistics usually doesn't make reference for the examples to hydrology or water, but makes reference to processes that are characterized by a clear random component. And in this case, the example is called the Gambler paradox. Gambler means giocatore d'azzardo. Of course, gambling is subject to relevant uncertainty. So now let's suppose that a gambler has to bet on the outcome of a random process. Bet significa scommettere. So let's suppose that the gambler has to make a bet on the outcome of a random process, whatever it is. And let's suppose that the gambler has an amount of money equal to capital D available. And let's suppose that any time that he bets, the bet is, the process is repeated. So he has the possibility to bet many times, like tossing a coin, for instance. In any case, it's random outcome. And let's suppose that he has to decide any time the amount D to bet, of money to bet. Of course, D is always less or equal than B. He cannot bet more than the money that he has. And let's suppose that the probability to win is equal 0.6. So it's more than half. And let's suppose that if he wins, he doubled. So if it wins, he takes an amount of money which